Okay, lecture 13, the inertia tensor and the substitution effect. I just met a number of members of the faculty in the corridor, and they said, wow, this one sounds good. This is the lecture I want to be in. And at the same time, I see that you guys are at least here. Some other, So there's a jealousy effect going on, because actually this has turned out to be a really interesting topic that's going to tie a lot of things together, both philosophically and mathematically and engineering-wise. At least this is one of these kind of topics are my favorites, when everything comes together, you know, in one picture of reality. So I could also have called this the metric tensor, because the inertia tensor is a metric tensor. Okay? Now, of course, you don't know yet what a tensor is, and I'm going to tell you what a tensor is, and I'm going to do that as part of this lecture. But a metric, you know what it is. A metric you use to measure something, the length of something. Okay? And this is an age-old function of numbers, is to measure length. The oldest is probably counting. Okay? And the second oldest is to measure distances. I mean, this must be very fundamental human. We humans, we walk around and we want to measure how far we are. So I can imagine these early humans counting how many steps they would take or things like that. Okay? And all of geometry, if you say geometry, there's really two words here. This is again the metric, right? And geo just means earth, I think, in Greek. Okay? Yeah, it is in Greek. In Latin, it's orbis urbs. Huh? So it's just how you measure the earth and we walk in. So all of geometry is basically derived from this idea. All right? So why is this important? Well, we have our normal space that we just live in, and I'm just going to draw a plane like this table in front of us. And we've been labeling these like this, but you can see X and Y, right? And we've been imagining, this is just our usual Euclidean space. Huh? And we've been imagining that this is, there's a commodity space, where rather than a distance, these are certain amounts of some commodity, so apples or pears or barrels of oil or whatever you want, okay? And we've been talking along as if these spaces are equal, but are they really equal, right? This space has, on the outset, a little bit more structure to it, because here, you know, this is measured in meters, and this is measured in meters, but this could be measured in number of apples, and this could be measured in number of pears, and it's not at all clear, you know, that these have the same dimension, how you would add them or do whatever, okay? So this space has a little bit less structure, and also you could say, well, that's the same as calling this centimeters or yards or something, but really not, because there's a conversion factor going from centimeters to meters or from yards or inches, and there's no obvious conversion factor here. It could be anything you like. How many apples fit in a pear? Well, I don't know, none really. They're not the same. Huh? Or how many barrels of oil fit into, you know, a haircut? You know, it's like, it's not so clear. So this is one thing, right? Now the other thing that you may say is that if I'm in Euclidean space and I have 2 points, here's one, A and B, I can measure this distance here, right? Now, if I have 2 points here, can I measure this distance? Well, what's the distance between, you know, a bundle of 2 pears and 2 apples and 5 and 4 or something? You know? Okay. So, on the outside, this space, Euclidean space, has a lot more structure that you just get for free. And it is in this structure that Newton formulated his law. So he assumed this structure. Nowadays, we would say the space is homogeneous, isotropic, So homogeneous means that all points are the same. No matter, you can shift the whole space, I don't care where I am. I can do my experiment anywhere, put my mass anywhere. And isotropic means all directions are the same. Okay? Now this space, I don't even know it's homogeneous. I can assume that, and we did. But isotropic means you have a notion of direction, and we don't even know what direction is. You know? Well, we can kind of say a direction that's like a certain proportion of a bundle, but would it be the same in this direction? You know, it's a little bit unclear. You don't even know what a rotation is. You don't know what angles are. You don't know any of this. All right? Okay? So this lecture will be about how we can take these geometrical notions that exist in Euclidean space and that we are so used to dealing with when we deal with Newtonian motion, and see under what circumstances we can get something similar right here. And it's actually a really fantastic trip, because when you get down to the details like that, all of a sudden everything becomes clear, you know. Now what is not so clear here? You may think that it's totally clear that if I want to have a distance, say, between 0 and this point, that all I need to do is take q1 square it, add q2 square it, take the square root, and that will be the distance. Okay? You've learned this, right? And why? Why? Nobody really asks themselves the question. In fact, there are people who ask themselves the question, and Emil, I know you're one of them. You're saying, well, Einstein certainly didn't agree with this, right? And he was right. This is not correct. You know? It's not correct. So this appears to be kind of correct for Euclidean motion. So the question arises, why do we assume this is the case? Okay? Where did that come from, this idea? And why does it work? Okay? And the challenge I have given myself for this lecture is to say, if we can figure out how you can do this in Euclidean space, then maybe we can, you know, we're good economic engineers, we can imitate that method and do exactly the same here, and then we'll know how to measure distance there. All right? And then we can talk about commodity space as if it's Euclidean space and the angles and this, and we also will know when it applies and when it doesn't apply. All right? So we're going to get to the bottom of it. Okay, this is kind of and in between we'll get to Quinton's inertia tensors and mutual inductances. We'll get to Emil's hyperbola. We'll get to kinetic energy. We'll get to Hamilton Jacobi equation. It's an enormous journey. All right. So we can probably do it in a little bit. I won't give you the details, but you'll get a different kind of insight of where all this stuff comes from and what the meaning is, especially of kinetic energy. All right? So before I start, just some intuition. Suppose you didn't know anything about the distance of everything, and you had to calculate the distance between 2 points. What would you do? Right? You're a primitive person, knives and bearskins and everything, and you want to tell somebody how far it is to go somewhere else. All right? What would you do? I mean, give me an idea, Rumer. Huh? Just walk there, right? So you count the steps, right? One step. No, you do one step, sorry. I'll do the steps as a vector, right? So 1 step, 2 step, 3 step, 4 step, 5 step, right? Yeah, that's a good start, right? This is actually where you can also count hands or feet actually, right? Yeah, that's where the word foot comes from, eh? Or you can actually, if it's smaller, you can put your thumb. That's where inch comes from, or thumb, right? Duim we say in Dutch, yeah, for an inch, yeah? Or you can take your arm when you measure cloth. There's an L, I think, in Old Dutch, right? Huh? Okay, so you start counting unit lengths, huh? That's not a bad idea, right? And in fact, the speedometer in your car kind of works this way, right? No, not the speedometer. The speedometer will know how fast it's going, and then you just count the number of
Rotations.
Yeah, this rotation is a little bit different, right? So the count, the number, this is just the velocity of the car, you know, and then you just sum them up over time, right? So you probably integrate, and then that's what you call distance, right? Okay? So this is significant. You would think you would start with distance and then define velocity, but really you don't. You start with velocity and you integrate it out, right? Right? And in fact, this is correct because Newton tells you this first law. You really know only going with a constant velocity. So you take that constant velocity, you calibrate it, you can say 0, then I'm not moving at all. That's just what I define, the no movement. And then whatever it is, I just sum this out, and then I have the distance, right? That's what Google Maps will do and all this stuff, okay? So you're just laying all these vectors together. And of course, if you just keep the velocity constant, you can multiply by the time that it took. And presto, you got your answer, right? Now, what if I go like this? Then I can do the same procedure, but am I going to get the distance between these 2 points? No, right? I'm going to get some huge number that is definitely bigger than the distance. I can do this. I can do this. But all of them will give me a number, right, say S, that is bigger than the actual distance, right? So how would I define the distance? I just try everything and I take the minimum, right? Okay? Simple. That's what you do, right? And that's what you call a straight line. Easy. Okay? So calculating distance is also a way of minimizing. You just try a lot of stuff. You got some way of determining what the total distance is based on your velocity. You just try it all, right? And once you try it all, you just say, okay, that's the minimum. That's what I call the distance, right? Okay? Now, this is a great idea. Why is this so great? Because suppose this is not a flat space. Suppose you're on the Earth, right? And then, I don't know, you have some dimensions. Here's Q1, here's Q2. I don't care how you do this, right? Right, some angles. Then you can take 2 points here, and you can find the distance. That's not called a distance. Yeah, that's called a distance, okay? Distance. Now, there's obviously not going to be a straight line because you're not going to tunnel through the Earth. You just confine to the surface. But you can do the same procedure. You just try a bunch of stuff until you get one that is the smallest, and then that's that length you call the distance. All right? So when you do that, you see that this whole business of using your thumb or your arm is not so great because you can do anything, and you really need an infinitesimally small meter and stick, right? So this tells you that you really want to look indeed at the velocity that you're doing, right? Okay, and you have to take the direction into account and the speed. Now, this is how you can determine a distance. There's one way. This line is then not called a line. This is a great circle, but in general, these things are called a geodesic. Okay? So you can have another manifold, say, here's a fun one. It's a hyperboloid. And you can walk on there. It's a big bowl like that. This is a hyperboloid I try to draw.
Oh, yeah, like that.
Yeah? Because I have two asymptotes. The paraboloid will have this one asymptote. And then I can define the distance between those 2 points, and it will also be a geodesic. All right, and they won't look like this. That's for sure. Okay, so if I look at the Earth, the Q1 and Q2, I'm not going to get this formula. Okay, So this is already number one. Don't get stuck on this formula. You know, figure out what your procedure is, and from the procedure, well, maybe not follow some closed formula. All right. the idea of length is a little bit more general. Huh? All right? Okay. So where are we? We're at the point that when I'm going along a path, I have to look at this tangent vector v. And that tangent vector will tell me how much I've traveled. Okay? And so I need something that depends on this tangent vector, right? That will tell me the distance per unit of time that I travel here. Okay? So I'm making a small excursion here, but I could have done it this way. And so if I draw a little circle, you know, that will be all the equal distances that I can do at this point. Right? If I'm going on this particular path, I will take this little vector out of the circle, and I'll call vectors that have this length, they have distance 1, right? Okay? So at any point, I can draw a little circle, you know, with all these possible things, and then I know this is the distance 1, right? Okay? So what was the equation for a circle? Well, what you'll need to do, if this is v, you still need to square the v, right? And then have a measure of distance, okay? Now, I can multiply by any number, still have some measure of distance, right? And I could divide by 2 too, okay? The measure of distance, right? Okay? Now look at this expression. This is the kinetic energy. Kinetic co-energy, right? So, the kinetic energy in Newton's framework, you know, where P is mv and all of that, right, is a way of measuring distance. If I integrate out the kinetic energy over a path, you know, I can get a distance. It's a square distance, I take the square root, right, and there is a factor half. I multiply by square root of 2 somewhere, right? Huh? Some factors. You look worried all of a sudden. Huh?
Yeah, can you repeat what you said? Because you called, you made the p of a vector of unit 1.
Yeah, so at any point, I want to know what a unit distance is, right? Huh? So I draw this vector, right? Now, this is what I call a unit vector, right? Huh? So this is the, so what are these points? Well, if this is the point 0, then these are the points where the distance, oh, this is q0 and this is q, at q0 minus q is a constant, right?
Yeah.
So this is what I defined exactly to be the distance. There we go, right? So the circle gives me a measure of distance in Euclidean space. By definition, almost. Yeah. So you can also say what is first, equidistance and then the circle, or you can say the circle is first and then equidistance, you know? Huh? What I'm trying to turn it, thing is, you got to turn this thing around. You got to say, I know what a circle is, right? And then I know I'll define that to be equidistant, right? And this works for Euclidean space, and for the Euclidean space where the kinetic energy happens to be that circle, right? It's the kinetic co-energy, right?
But it just feels like you cheated your way into saying that kinetic energy is a distance just because it has a squared term in there. I could have taken any equation with a square in it and just told you this exact same.
Yeah, but they'll be the same up to a constant.
Yeah.
So it doesn't matter. I mean, inches, centimeter, I don't care about that, right?
Yeah, but I can just take any formula in physics.
Yeah, you could take v to the fourth.
Somewhere.
Yes.
And then say.
And call that a distance.
Yeah.
Except we don't. We take a quadratic one for the distance, right? And my question is why? Now, one way is to say, well, we didn't have this notion of distance. What we had is a notion of kinetic energy, and that we call the distance. You see? If you had another expression for kinetic energy, which you will on the sphere, you will get another notion of distance, and that would coincide, by the way, with the right notion of distance then. You see? So I'm not cheating, I'm turning it around. I first asked you the question, where does it come from? Nobody has a real answer, right? Then I say, well, maybe it comes from the kinetic energy. Now, then I ask you, what do? I ask you, well, you go to a car, and you see how fast you go, so you have constant kinetic energy. Huh? And you just kind of, so it's kind of built in the way we measure it. That we have this velocity, and we're keeping it constant, right? Because if it's changing all the time, and we don't even know it's changing, because we're in equilibrium, right, then we would just say it's not changing, right? So Newton tells us when we're in equilibrium, when the velocity is not changing, right? Then Newton allows us to calculate a quadratic form that we call the kinetic energy, and by our reasoning, that is precisely what we need to use to measure distance. You see the reasoning? See, you're stuck on the idea that you first have distance and then kinetic energy, then it turns out to be quadratic.
No, I'm just stuck on the fact that it seems like just because we have velocity squared in there, then you're calling that a measure of distance. But if I take some temperature, some function, I can't think of something right now, and as maybe a temperature square, then I could use the same.
No, but do you know that the forces are zero then, right? No. You got to know you're in equilibrium. Okay? You're cruising along at a constant speed, whatever that is. How do you know you're at a constant speed? You don't really know. You know there's no forces on you. That's what you know. Right? So I can recognize this thing, independent. Okay?
Although in Lipschitz, they just derived it based on the fact that space is isotropic and homogeneous.
Yeah, so
if you assume actually that your geometry is Euclidean, you have no curvature and it's isotropic and homogeneous, you automatically arrive at this.
Yeah.
It's the only metric that was.
Yeah. This is the problem.
Yeah. And the second thing is that metrics always act on the tangent space, so that's why there's a velocity in there in that position.
Of course they act on a tangent space because you want to make an incremental movement. Yeah. Otherwise you can't take a wiggly path.
You're not guaranteed to have a vector space anyway, so.
Yeah. That's right. So temperature is not a vector.
Yeah.
So you need the vector space, you need a tangent space on a space, and then you've got to add. So what you do is you do this, and then all you're doing, and this is what Rumer said, all I'm doing is adding up all these tangent vectors, right? Yeah. So I need at every point a tangent vector, so I'm in the tangent space, and then I know that equidistant ones are going to be but the energy would give me a unit for the distance, whatever the direction. I just pick them out, and I just count off, okay? That's what I do. So you don't need a metric, you need kinetic energy, and then you can derive the metric, okay? Now, if this reasoning can be applied here in economics, okay? Because here we will have some running costs, okay? And we have to figure out what they are, and then the cost will give us a metric, okay? The surplus will give us a co-metric, okay? So prices will give us a metric, that's kind of how long it is, but also quantity demanded will give us the metric, okay? And then the cost, the total length will be the total amount of cost associated with a particular type of buying and selling activity, all right? Just like the cost rate or the running cost is associated with what you accumulate here is the kinetic co-energy, all right? So there's a good reason, Jose, that I turn this reasoning around, because then I can apply it here and I'll get all the same results, all right? That's the trick. That's the trick. Now, it so happens that what may feel like a trick is actually not a trick. This is the real reason we have this metric, as Einstein realized, because you don't need to use a circle, you can use anything else. He used, instead of a circle, he used a hyperbola to measure distance, okay? And it worked. He got the right results. And when he has one axis is time and the other is space, for instance. You know, he couldn't use a circle, so he took a circle flipped inside out, right? That's a hyperbola. So if you have a circle, let's say you have a lamp at the ceiling, it gives you these circles, but if you project it on the wall, you get the hyperbolas, right? So it's, okay. This is the right way to do it. So motion determines distance. And the motion is what follows from our economic laws. And what we're doing is imitating this procedure for different types of economic laws. All right, that's the idea. Now, if this motion is very complicated, like for instance Quinton has with the substitution effect, the metric is just going to be more complicated, but it will always work. Okay? And then what you will see is that the motion of the particle will follow some line that is a minimum distance line. Or here, if it can't go around, it has to go around here, it will still be a minimum distance in some other metric. All right? And this is the key to minimum principles. Lagrange's principle, Hamilton's principle, etc. All right? Optimal control works like this, where the cost function is your metric. Right? And then it's a question of a little bit of calculus of variation to show you that the two approaches, Newton's laws in Euclidean space and this thing, are the same. Okay? All right? But here, this lecture, I really want to give you that intuition and how we can build it up, the metric, and endow our commodity space with this, this extra structure of distance, and then use this distance to our advantage to interpret it economically and do expenditure minimization, profit maximization, all these things, and get the right equations of motion. All right? So this is a hideously interesting topic, and before I launch into it, I actually want to immediately talk about an alternative way of measuring distance. So the way, what Rumer gave us was really what you would do if you're like primitive man walking around before the invention of the wheel. You know, that's what I asked for, right? But now, suppose I know the Egyptians did this. You're an Egyptian, right? Ancient Egyptian, building these pyramids. How did they measure distance? Did they also go like this? Actually, they didn't.
Use the sun.
Yeah, but just to measure distance in the desert. I give you the key, the wheel has been invented. All right? Now, what? Yeah, so you get this little stick and you count revolutions. You already said it with the car. You start counting the rotations. I think that's how a speedometer works, actually. And actually, not the guy that the police has or Google uses a satellite. You know, it looks at your speed. But the internal one of the car just...
You can see it very, very easily if you put a speedometer on a bike.
Yeah. And then you start standing still and you're turning the wheel. Exactly. Yeah, or if your wheels are slipping in your car, it will still measure the, Yeah, that's right. Yeah, that's right. Yeah, in the old days, when I was a kid, when you wanted to gyp somebody and sell him a car and pretend that he had done less kilometers, yeah, so they put a little electromotor on the thing and rode it back. I don't think.
Actually, she would drive forward somewhere and then drive backwards so that their parents wouldn't see it.
Oh yeah. But in the old days, you could decouple it and then they go, hey. So now I don't think it works so well anymore, but that driving back will still work. So, all right, now I want to say something. So now you're going this distance, right? You're doing something, you're going along a line, but you're not like putting these little meter sticks out. You're counting rotations, right? So what you're doing is something a little different. You know, every rotation, you make a little mark, right? Okay, so I guess when you go fast, what if you go faster and then the marks get a little closer together or not? Or did they go farther apart? They got closer together, right? I always get confused. Yeah, view, huh? Doesn't matter now, no.
Just normal. You can
No, it doesn't
Yeah,
appear like.
doesn't matter, yeah, it doesn't matter, right. It depends how you count. If you count in time, then it will vary. But the other thing you can do, rather than laying out these meter sticks, is to make these, hash marks across, right? With the direction saying what is the positive direction. Every time you put a little piece of chalk on there, on the ground, and you just count those things. Huh? So you're not really doing this, you're kind of doing this, all right? That's another way of measuring length. Now, why do I say this? Because there are two descriptions for every movement. One is what we call the particle description, and the other is the wave description. And we'll see in this lecture, if there's any time left, how the two will interact, okay? So the particle, this does this. And the description that the particle is over here, or here, or here, and this is its velocity, right? And this is what Rumer said. Now, I don't know who said that, maybe you said that too with the wheel. That's quite different, right? We don't have any particle, we just have a wheel. What is the wheel? This is the whole thing, and maybe an axis somewhere, but that's out there somewhere, right? Huh? So there's no particle. But instead, you can see, like you could roll the wheel that way, and you can get like these big circles, okay? They look like a wave spreading out, and this is called the wave front. Huh? So you can imagine different Egyptians with these wheels, one going this way, along this way, one going along that way, and they're just counting off, and it will make these big circles like this, okay? So you can think of this distance as being measured as a wave, okay? So you're counting, so this is 2 pi r. This is one revolution of the wheel. I believe that's 2 pi r, right? Huh? Okay. And you're just counting these revolutions, right? And that's what everybody does. So instead of going along a path, like as if it's a particle moving, we just think of a wave going through space, okay? This is sometimes convenient with light. You can't really see it, So Newton, he added that it was a particle. He called it a corpuscle of light. Now we call them photons. But they're hard to see because your eye is the one that sees them, but it needs a whole bunch of them in order to find one, right? So no wonder Newton didn't see it, okay? So, but nevertheless, they're there, and Huygens, he figured out that one way to describe this was rather saying this guy is doing that, and that guy is doing that. He says it's just a wave. And they're all like, so you're sitting here with your flashlight, right? Huh? And it's all going every which way, but what I'm doing is I'm, showing you where the wave front is coming out. Or I have a puddle of water here, I make a big splash, and you just see this wave moving, okay? It's totally valid, right? You need to invent the wheel. That's it, okay? So once you have the wheel, you can write down stuff like this, right? Because this is the wheel. Now you really have complex numbers, right? So you can turn 90 degrees, and then you have wave mechanics, right? Now, you probably have heard all this. There's a discussion about whether these are particles or waves and this, and you kind of see from this it's kind of irrelevant. You kind of have a different description, that's it, right? And so it is in economics. It is kind of irrelevant. So you can see the behavior of an agent as being, here's that agent, and he's got his demand, and now the agent's got this stock, and he's doing that, and he's transacting. But you can also think of it as a wave. It's just like more an accountant will do it. It's just his costs are just spreading out over time, all possible directions, And the thing is, where is he? How much has he accumulated in cost as this thing goes on? So he goes through his business cycle, and he's accumulating these net sales and accumulating whatever, and you see it more as a wave, all right? Now, there's a theory that deals with this, and that's called Hamilton-Jacobi theory. Huh? And they are the same description of Newtonian mechanics, but now the whole thing based on the idea that you just have something spreading out over time, okay? Accumulating distance, okay? That's it. Now, end of lecture. This was all of Hamilton, Jacobi, and metrics. Now, not the end of lecture. We're going to go on, and we're going to go through some details and show you how this relates to the inertia tensor, elasticity, cross elasticities, etc. Okay? And then I want to end on this kind of different picture, you know? And then it's just my intention is to bring everything together. These are some of my favorite subjects that you can just think of all of it in such simple terms. So we're okay now? You're okay too? Yeah? You're usually quite critical, which I like. Huh? Oh, you're the only physicist. Yeah, I mean, these engineers, they just, they move on, right? That's also good. Yeah? So,
sometimes better.
Sometimes better, yeah. Sometimes the bridge breaks, you know. Well, they don't do anything new. They just move on and they come to somewhere where everybody's already been, you know. Oh, I lost my... I think you clicked on... Ja, want je bent naar OBS zit actief. Op het scherm, hè? Kijk. Nee. Brit. Ja, het is er al. Ja. Ja, en nou moet hij werken, hè? Ja, nou werkt hij. Hè?
Als je toch bent, zou ik even in Teams de microfoon wisselen.
Oh ja? Welke microfoon heb ik dan? Heb ik de verkeerde microfoon?
Nee, in Teams staat die. Ik kan niet op laten doen.
Boven? Ja. Microfoon.
Camlink.
Ja, even de camlink, ja.
Welke is dat?
Oh ja, die ja.
Digital audio interface.
Ja, die.
Is het beter?
Is dat beter?
Ja.
All right. Okay. So after this long introduction, right, I can go fast for this stuff. Okay? So here you see there's a nice space, Q1, Q2. Just think of this as a particle. Here's the particle, right? It's moving at this velocity, you know? Now, what is it going to do? The particle has a mass, m. It doesn't make any difference for Newton whether this mass acts in this direction or in this direction. Well, if there's no gravity, there's no difference, right? So Newton can just write that the momentum of particle 1 is so I just wrote it like this, right? Fine. So I also wrote, so the momentum, you would normally learn that it's a vector, okay? It actually isn't. It's a covector, okay? And the reason is that this vector can act on this covector through the inner product and give you the kinetic energy, all right? So if you take mv1 and you multiply it by v1, right, this way you can get this. You can figure this out, okay? So geometrically what you do, if you want to calculate this action, you take this vector v and you see how many times it fits in p. This is 1, and then maybe 2/3 or something. So this is 1 2/3, and then you multiply that by half, and then you get the kinetic energy. All right? So you could also do this with an inner product, and the p would be somewhere here. Then you have to do the projection, or it would be here somewhere, I don't know. Probably here. You do this projection, and you don't know. This is a little nicer. Why is this nicer? Because suppose you don't have a metric, which we don't have here, because this is now some commodity space, this still works. You can just count these hash marks. All right? Okay? So this is just your old Newtonian approach. Now, what is wrong with this? Okay, now the first thing that's wrong from why this is inapplicable from economics is why the heck are these two equal, right? That's certainly not the case. I mean, I've never really worried about it, but why, if this is apples and this is pears, and why would my price elasticity be the same? you know? So they can't be equal, right? So in economics, we certainly want, you know, these to be different, okay? So you can already see this Newtonian framework is pretty limited, you know? Really is limited to like looking at one commodity at a time, you know, then doing a transformer and then looking at another commodity kind of separate, you know, with a different mass. And if you put them together, you might want to put them M1 there, M2, but you can't really view it in Euclidean space like that, right? There's no good fix for it. So already this framework that Newton worked in with his 3 dimensions is not so applicable, right? But let's analyze it first. So when I generalize, at least we know how the mechanism works, okay? So you remember I talked about this kinetic energy. How would you calculate that? Well, you would first calculate the momentum. Then you would look at the inner product between these two, right? You put a half in front of it. In matrices, this stuff, and there you are, right? Okay? So this construction I plotted here. So here you will see the same vector, you see the same momentum. And how do you find this momentum? Well, this is the metric tensor. So this is this M as a whole tensor. So now this is I. This should have been I. Huh? Then what you do, and you can figure out at home whether this is right, you take your vector, and you from here you draw the tangent to this circle, and then you find 2 points. And through there, you draw a line, and then this distance gives you the momentum, okay? So the unit vector will give you a unit momentum, right? And you'll get that here it's 1, and here you'll see it's 1, and you know, and something, huh? Okay? This is just how you do this geometrically. So the way it works, these things, is this is what they teach you, right? This is the one I hate the most. Yeah, what's going on? Why is this a row vector? Why is that a column vector? Why is this, you know, what's this all doing, right? I hate it, right? And then you get this. This one I like it better, because at least I know I'm acting with this and that, and you know now, huh? This one I don't like for the same reasons that, but this one I like better. But this is what I like the most, you know? And then the translation of this to that is immediate. I recognize a vector as a directed line segment. I recognize this covector as this set of lines, sort of a gradient that I'm going through, right? Huh? And I recognize this thing as being that circle, okay? This thing is called a tensor. This is a vector. And this is called a covector, or one form sometimes, but that's a stupid word. That's what it, huh?
The vector and the covector are also tensors, right?
Yeah, everything is a tensor. A scalar is also a tensor,
yeah.
Right?
Yeah.
But this is what this is a 2-0 tensor. And a 1-0 tensor is a vector, and a 0-1 tensor is a covector.
Yeah.
So the order, you look at the order. In matrices, a covector is a column, a vector is a row, is a covector, a vector is a column, and the matrix is a tensor, all right? Not every matrix is a tensor, but every tensor is a matrix, okay? This is important. Why do I call it a tensor rather than a matrix? Why did I call it a vector rather than a column? This is a question. In math, you learn a vector is a column, right?
Numbers say, I think.
Yeah, a bunch of numbers here. Huh? What's a vector? Here, this is a vector. Has the Dexter actually do it? Okay, but this one, you can kind of, This one is real. This one is what we call invariant. That's the term we use. This one depends on your coordinate system, right? So if you take a different coordinate system, you've got to transform this vector to get, yeah, this is now a transformation, not kinetic energy, right?
Oh yeah.
Yeah, Larry? So this thing will also transform. You know how you do the sandwiching, t, and then this m, and then t minus 1, and all this stuff. So this thing depends on what coordinate system you choose. But if I draw this, where's the coordinate system? There's none. It has physical significance, right? So this thing is just what it is. This thing is not what it is. It's going to depend on the coordinate system I choose, okay? That's the important thing, right? So that's why I like this kind of thinking, because here it's all dependent on what coordinates I chose. Then you have to like undo this all in my head. Here I can just think about it physically or geometrically, all right? So physical or economic things are what we call invariant. They cannot depend on the arbitrary coordinate system you choose, all right? And invariant thinking is a very important skill because it cleans up your thinking. Otherwise, you're sitting with all, as soon as you see all these subscripts, you know you're in trouble, you know? Because you have to like, do all these coordinate transformations and blah, 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 and then you finally kind of figure out what's going on, right? Okay? So this tensor vector covector focuses more on the nature of this thing rather than a particular representation as a matrix or a column or a row. Okay? At any rate, so for this very simple system, you can see how the equations you are used to, you can express them very simply in this way, and you can do the geometry in this simple way here, okay? So this here is the tensor, this is a covector, this is a vector. So think of a vector as an arrow, think of a covector as a gradient, right? So there's a mountain and you're walking up, and all you're doing is straightening out the level lines. And think of the metric, the tensor, as a little circle around yourself. You know, that you take your arm and you can sweep it around, and that fact tells you that you know what a step is. You can take a step in either direction, right? And the step gives you the tensor, right? Because you can turn. Huh? So with your foot, if you keep one foot stable and the other foot like this, you can see that the step idea is translated in a circle. And the circle is invariant, right? It's just a concept. Okay? You guys follow that? I want you to get the picture of the geometry in mind. So we're going from steps in physical space to simple objects in geometry that the Greeks already knew, right? Little line segments, little gradients in circles, right? This is a step you got to make. Then everything becomes easy. And even stupid people like me can do math, all right? Huh? And science. So now we've got this nice picture here. Everything is looking hunky-dory. We hate this, but we know how to do it because in actual calculations, this is what MATLAB does probably. It has no idea about all this. Huh? I mean, computers are silly that way, but they're really good with coordinates. And ultimately, you need to do the calculations in some coordinates, all right? In the old days, we would do it all by hand, and then I think our thinking just got stuck on this as being the real thing, but it isn't. This is the real thing, and this is the real thing, okay? This is symbolically just says this, all right? And my feeling is that was just in my day that we got all these computers that could only do these symbols, but now if I look at graphics, there's no reason why we can't go back to geometry as the main way of doing math, okay? It's just that we don't have the tradition. We lost the tradition. I have to go back to the Greeks who were like the ancient Greeks who were doing in the sand. All right, so this is a particle. It's obviously insufficient for purposes of economic engineering, right? Not totally, because you know, you can do one dimension, that's already quite something, you know, because a lot of our bond graphs are just one dimension, just deal with oil, you know, or just deal with whatever product. Huh? But quickly you'll. So let's move on. Now, for some reason, I lost again my. Yeah. Oh, too bad. Here. So the one before is what you would call isotropic space. It's the same in all directions, you know? So Newton, you see, the mass is the same in all directions, so it's isotropic the space. Here we look, the main, it's always anisotropic. So the directions are different. They look different things, okay? So this equation that we had with zeros here has to be replaced by something else. Now, one step is when you set d is equal to 0, you just have two different masses. But let's just go whole hog here and just fill in the matrix, okay? So this thing works like that. In fact, you probably know from matrix calculus that it's a question of a simple transformation to get this thing to be orthogonal, right? Now, diagonal matrix, okay? So once you got these things unequal, then you can do anything you want, right? So you just get this thing over here, and the calculations are just, I mean, in this here, nothing changes here, right? Here it gets a little bit more hairy because you get this cross term. You get these are different, huh? But you know, here nothing else different. Now what changes in the picture? Right now, instead of a circle, you get an ellipse. Right? So the ellipse has got like these two principal directions. That's when you rotate the thing that there is a 0 here and here. Right? Now here I drew it that it wasn't, so I haven't aligned my coordinate system along the principal directions. Okay? You should know all this stuff from elasticity tensors and all kinds of other things. Right? Huh? So this is my new metric, right? So here is my new inertia, and the inverse of that will be my new elasticity, right? And now it just looks like this. And how do I go from a velocity or the quantity demanded to the price? Well, I do the same thing, actually. I'll just do this and this. And then presto, I have the price. Okay, so you see that they're not orthogonal anymore, right? You know, they point in like different directions, okay? So your momentum or your price is not pointing in the same direction as your quantity demanded or your velocity. There's no problem, it just so happens to be the case, right? So the wavefront is kind of moving like this, but you are going this way, all right? So the guy with the wheel, he measured this way, and you with your little meter stick, you went another way, all right? Okay? But nevertheless, you can see that the inertia, this is called the inertia tensor, right? And again, it's invariant. I could have chosen this as V1 and V2. This ellipse is just an ellipse. This thing says it's totally invariant, right? And these tangent lines will just remain there, all right? So it's a very pretty picture. You know, that just summarizes what's going on. You look a little worried, huh? Yeah. Yeah. Okay, good.
Should the V vector be orthogonal?
No, that's the whole point. That's only the case when this thing is a diagonal matrix. Huh? That's the whole point, that it's not orthogonal. Right? So you may know this. If you take, you see, the problem is you can't imagine a mass, because a mass is always the same in every direction. So in mechanics, the best you can do is imagine a potato, right? There's a rigid body in space that's rotating, okay? The center of mass motion's got the same problem as a particle motion, so it's rotating, right? Now you press on it to go this way, right? Then it may start rotating a total different way, like a gyroscope, okay? Huh? Or a top. You can have a spinning top and it tilts over and gravity is acting like this, you know, providing a torque like this, and the thing will nutate and spin off in another direction, right? So the momentum is not perpendicular, or not even, yeah, no, it's not perpendicular, not aligned with the velocity. So the perpendicular of the level lines is the same as the alignment of the momentum, right? Okay? And you can see the geometry of the cigar gives you precisely that, all right? Huh? So if you look at an ellipse, it has some central axis. That's exactly what you get when you orthogonalize the matrix, okay? And it has this squeeze, which is exactly what you get when you don't have M11 equal to M22, right? So there's a way of rescaling this thing and then pumping up one of the V's so that you get a nice circle, sure. But it will totally depend on the coordinates. So suppose you have some demand, and these are apples per unit of time, and these are pears per unit of time. For any situation, you'll be able to redefine apples and pears, number one. Number two, define little baskets of apples and pears because you got to rotate. That means that I got to give you a basket of 2 apples, what is it? 2 apples for 3 pears, and then minus, you know, you have to get the orthogonal one, huh? So I can't work with apples and pears. I have to work with little fruit salads, you know, and they will be orthogonal then, right? Now this sucks, right? Why would you want to do all that effort and then describe what's going on? No, you just want to deal with this, okay? Right? So what you know is that the kinetic energy is calculated in the right way. The price is now not orthogonal. So what happens is the demand for, what is it, Clinton, hydrogen, you know, changes the price of, what's the other one? Huh?
Diesel, for example.
Yeah, diesel, right? So this is hydrogen. This is the price of diesel. So you got demand for hydrogen, you know, changes the price of diesel there. There you go. Now, demand for diesel changes the price of diesel, and you know, and you work your way out. Huh? And of course, Clinton can do a rotation of the coordinates so that he gets mixes of hydrogen and diesel where everything will look perfectly orthogonal, and he won't have any substitution effects because he has the right mix. Okay? All right.
This figure, how is the momentum co-vector drawn? Because it looks like 2 parallel green lines.
Yeah.
One of them going through the center of the ellipse.
Yeah, that's how I do it, yeah.
And the other one looks random, so is there...
No. Okay, so if you draw a vector, you have a 0 point where you anchor it, and you go out here. Is this point random? No, not really. I mean, this is just the value, right? Now, you can draw a vector also like this. That's all.
Yeah, and what I mean is, so the direction of the co-vector, is that along the momentum?
No, that's well.
So the direction of the co-vector, how is that chosen?
Well, if you act on the co-vector with the vector, you'll just count this off, okay? So this is the picture. You're a hiker, right? Now in the Netherlands, we don't have any hills, but you're going up the dike. Or you're from Belgium, they have the Ardennes. Or in Suriname, they may have some mountains. So what does that mean? Here you have this mountain, right? So you know how you can draw these mountains with these level lines like this, right? Huh? Now, suppose you're hiking, right? So I should have drawn the one in green and the other in, huh? So I'm going like this, right? To the top, right? So at this point, what's going on, right? Well, the local direction looks like this. I'm walking, right? Huh? This is the tangent, huh? Okay? But how fast am I going uphill? Well, I'll just do this. And this is a step upwards. right? So I take the equi-height lines, how do you call those, contour lines,
Yeah.
and I just straighten them out. So that tells me how many meters I go up. This tells me how many meters I do per second. I put them together, right? And I see exactly, you know, so I count off, that's one, and then a little bit. All right? You follow that?
Yeah, so there on the left, what you do, I follow that.
Yeah, and here, same thing. So this is so that's how far you climb up the cost mountain per unit. And this tells you how far you go per day. You multiply them out. And then you'll see, it will tell you how many dollars you acquire per day. Here, when you climb your mountain, it tells you how much altitude you gain per hour or whatever, right?
Yeah.
Or per day. That's all. So the cost on the mountain that you're climbing, that's why it's so natural that it's a covector, because it feels like a gradient. You're going up this gradient, you know? And what speed are you going up? Okay, I'm going at this speed, right? That's my quantity demanded. But this quantity demand is going to hit the price as if it's a mountain. You have to, you know, a mountain of cost, you know? A better cost amount.
Right, so in this picture, if you like rotate the like the covector will also change place, right? So the mass matrix is invariant, so to say.
Yeah. So if you put the vector here,
Yeah, that would also be
so you draw the tangent line,
yeah, right, exactly.
and then
Yeah,
Yes.
so I think some people may like assume that the p is also like an invariant thing that is like set in stone, but it's
well, what does this say? You take the I, you give it a V, and it gives you the P.
Yeah. No, I get it.
Yeah.
It's like,
Yeah, but you may think that, but that's not what that says, huh?
yeah.
No, it's a good point, huh?
Yeah,
Huh?
I think if people think about the map, they see like the peak as like or a gradient that is tied to a position that's like fixed in the Q1, Q2. In this
I mean, the mountain is fixed. That gives you these lines, huh? So this is your mountain, huh? But it's a valley actually. Here the cost is 0.
So you drew the tangent lines with the inertia tensor.
Yes.
And that's how you
Yes.
the second green line.
Yes,
And the
yes,
first one is
yeah.
parallel and going through the center.
Yeah.
Yeah, that's what I wanted.
I mean, suppose you're standing in this big valley and you want to go up, right? Huh? So you draw these, you have this circle around you, which is this sort of cigar. You just draw these, you know, and then, okay? But then if you walk that way, you're going to see something else because you're in the long part of the cigar, and that way you're going to go up steeper. So you've got to tell me both. You're going to go to a particular velocity, and then given the ellipse, I can tell you how fast you'll be going up the mountain, right? This is a mountain of costs that we're climbing up. That's why this picture is so illuminating. You see everything, you know? Huh? The problem is we don't have any mountains in the Netherlands, but we do have a lot of costs, so. Huh? That's right. Yeah, sometimes when I see these things, I just see them, and then I forget to explain the obvious, you know? But you will have the same problem. Once you see this, you kind of go like, well, this is a good picture, right? Huh? I mean, this is a complicated object, this inertia tensor, so that you can just write it down and figure it out like this. This is kind of like, huh, what? Huh? You know? So, let's see. What I think I should do now is take a small break. And then still have a few slides. This is the last slide. So let's take a break. I'll just leave it on this slide so you guys can ponder this one, and then we'll put the video on pause. Don't stop it. Huh? Put it on. Okay.
En dan weer daar klikken.
So what I want to do now is just quickly, we did all this work now, we got it all in a nice geometric picture. Just want to quickly reiterate what we have here, just the kind of math that you may see, and I like to look at it. So we can now define for economics, they don't really work with inertia, they work with the inverse of inertia, right? So normally we define the elasticity as 1 over m, and now, of course, we'll need to define the elasticity tensor as the inverse of the inertia tensor, right? Okay? So if it were a matrix, you would just calculate the inverse of this matrix. Okay? Now, why do we call them tensors? Well, okay. A vector and a covector, they are linear operators. A vector acts on a covector, we've seen that. The momentum or the price acts on the quantity demanded to give you the surplus or the kinetic energy. So they act on each other and they give you a scalar, right? So you can see this as being the price acting on this velocity to give you a scalar, right? I think it's twice the kinetic energy, huh? Okay? This is a scalar. It's a number. Also, but then there's a difference between a scalar and a number, right? A number, this is a number. But this will change with the coordinate transformation, or with this V1, say, huh? Or M11. Huh? That's a number. It's not a scalar. Why? Because if I have different coordinate transformation, this will go to V prime 1, right? But this is a scalar. If I do a coordinate transformation, I'll get the same value of the energy. So scalar,
That's not true, right?
if I keep my inertial reference frame fixed, right? So I take my inertial reference frame, huh? Yeah. And I just do the whole thing in a rotated inertial reference frame, right? Then I'll calculate the same kinetic energy. Okay? If I give this whole thing a yank, that's an affine transformation, right? Huh? Don't do that. Huh? We're looking only at linear coordinate transformations. Okay?
And what did you say earlier? When does the velocity change? So the V1, it becomes a V prime. Under what condition does that?
Yeah, so this vector V, that I've just done with a small v, is in a certain coordinate system is this.
Yeah.
Now, these are numbers, right? This is also a number. This is a vector. Now, suppose I do a transformation. What's going to happen to this vector? Well, it's the same vector. But now, it will be equal to V1 prime, V2 prime, right? Okay? This is in the prime coordinates per system, right? So, V1 is not invariant.
Yeah, but again, this feels kind of like, because the V1 is a result of the coordinate system that you've chosen,
right?
And the V velocity itself changes in the same way that the kinetic energy, for example, would change, because it's only
no. The point is
it only depends on the reference frame.
Yeah, but the point is it doesn't depend on the coordinates you choose. You understand? Isolate the effect of the coordinates. The coordinates are arbitrary.
Yeah, okay, so you're calling the V1 just a number here. That's
Yes. A scalar is a number that is invariant. And invariant under what? Under admissible transformations. What are admissible transformations? Changes of coordinates. Okay? So in Euclidean space, a rotation. Okay? Or an expansion in one and a contraction in the other. Right? Huh? Okay? Huh?
Yeah.
So this V is invariant, and these are, so a number that doesn't change with change of coordinate system is called a scalar. Okay? I just want you to realize there's a difference between a scalar and a number. A scalar is a number, but not all numbers are scalars. Okay? Okay? A vector, it can be represented as a column, but the vector itself is invariant. The column need not be, right? It probably isn't. So every vector is a column, but not every column is a vector. If I take some weird stuff, number of ozis here, and here I put somebody else's here, how is that going to change as a vector? It doesn't. You just have an ordered list of stuff, okay? So not every ordered list is a vector. Okay? This is just the terminology. what I want to do is I want to reason without having to choose a coordinate system. Otherwise, I sit with these matrices and I have to multiply all these matrices together. This is what you don't want to do. At least not people like me. I just can't keep track of them. So I think of the price as acting on a quantity demanded to give me twice the costs that I make. Okay? And how does it act on that? Well, just do that inner product. I don't care, right? Huh? Okay? Now, I also know that the price, before it acted on something, is I calculate by plugging in the inertia tensor the velocity, right? That's what this equation was supposed to say, right? So I can think of it, the inertia tensor, as acting on two having two slots. I plug in one slot, the velocity here, or the quantity demanded, I'll get the price, and I'll do another one, then I get the price here, and I'll get the kinetic energy. Huh? All right? So this is what we sometimes say, this is a vector, a tensor is a bilinear. It acts on two things, right? So if you look at this matrix, actually that's what it does, right? So it takes this, you act on it with one, here's another copy, right? Left multiplication, right multiplication. Then you get your scalar. It's just another way of saying all this stuff here. Huh? So here I only did right multiplication by the column. I still have to do now the left multiplication by the row, and then I get it. Huh? This is how you would see it in the tensor literature. Okay? All right? There's just some notation to get you used to this. So you can see this thing, if you take V, W, two vectors, and you divide by, you can calculate the angle and all this stuff. Huh? It's like an inner product that it gives you. Now the inertia tensor, elasticity tensor, is the inverse of the inertia tensor. So it will just act on the price to give you the quantity demanded. And the quantity demanded will act on the price to give you economic surplus. Okay? So whether you use the inertia tensor or elasticity tensor, it kind of is the same. This is probably the most intuitive, and this is what economists do. Because of Newton, we wrote this instead of what we should have written probably, which is this, because this is the independent variable, but no, doesn't really matter. Okay? So this elasticity tensor, this is exactly what you're dealing with when you're looking at the substitution effect. Of course, when you model it, you can model this. I stole this, or I didn't steal it, he gave it to me, Quinton. So Quinton here has a couple of flows. So here's a current going through. Here's another current flowing through. So he has this vector, F green, F diesel, right? And then he has this tensor acting on this, and then he gets this price, diesel up, okay? And of course he has to invert this, and then he has to invert this to get the elasticity, but that's a little thing, okay? So Quentin, are you happy? This is what you're doing, and this is kind of the general, I just wanted to give you guys the general framework for getting at this result, right? So this I cross, I assume, if I look at this tensor, is sitting over here, right? Right? And this is the I green, I diesel, and here's I cross again. By the way, these are always equal, as you can easily prove by looking at those figures. Okay? No, I think, no, they're equal. Yeah, I'm very sure. Otherwise, the matrix wouldn't be positive definite, would it?
I think
Yeah.
so.
Oh yeah, you need it for Sylvester's theorem. Otherwise, you don't have the principal directions.
Yeah.
And, stuff.
Yeah, you get another shape.
Matrix, certain parts of cluster where you have like real eigenvalues.
Yeah. You also need this positive definite, so this has to be bigger than 0. I mean, there's no negative kinetic energy. Okay?
Is there negative surplus?
No, not in this theory. No. No. There's no trade, but no negative surplus, no. Impossible. No, not in this theory. I mean, how do you calculate the surplus? There's this, right? And then the other way, both are negative. Well, so it's a positive definite tensor. So you know, I mean, look, you can figure it. What?
We find, I think if I say right, correct, then we define also kinetic energy with respect to another object. Because we define the...
Yeah, but either way, it's going to be positive. It's always positive. Yeah, I think you'll find that out. No, so either way, this thing is a positive definite matrix. You'll see that they're the same. And a metric also. There's no way of measuring negative distance with your metric. You know, how are you going to do that? Huh? I was like, what direction are you going to take to have a negative distance in your metric? Oops. Huh? Look, it's stuck. It's stuck to your chair here. Because of the magnet. God, you know what this is are. Huh?
A few weeks ago, we gave surplus another name. I wrote it down here. When you're done.
Yeah. What the heck? Surplus another name?
Yeah, I wrote here above surplus, I wrote profit.
Yeah.
But profit, you can have negative profit, that's just a loss.
Yeah, so the total profit will consist out of this, okay? That was a shortcut for a special situation. We'll get to this. Huh? You know, because it looks at your gross profit or net profit, you know? We'll see, that's right. So you want to be careful what profit you mean. This is a profit that's always positive.
There is, what did you say? There is a profit that's always.
This particular idea of profit is always positive. But you have all these different profits, gross, net, EBITDA.
A company that's losing it's losing all of its money. That's
right.
Not making a profit, right? So how would...
No, but it could also be, say it has a lot of, you know, a huge carry, you know, some benefits it's losing, right? Huh? You know, so you can subtract that from your, huh?
So the thing is, this way we only really look at profit from revenue, right? From selling something.
Yeah.
So you cannot make a loss from simply selling something.
Now, so here's, we're going to get to all of this in the context of Hamilton-Jacobi, okay? So I kind of don't want to leap ahead, but you'll see that this here is P times V. So this is P acting on V, and then this part is that the half must be this profit. And just because when this is positive, the price is positive, and the negative, you see that this is how it works out, okay? Huh? I don't know if the Gibbs free energy is the same, you know, so there's all these notions of profit lying around, you know. Huh? So it's probably best if I don't call it profit and just call it the economic surplus, and it's always positive. Okay. So here we are. So this is the kind of thing that anybody can do now. I think you also have a substitution effect, you know. All you do is you go to a high dimensional space and just be sure that you got yourself a nice, decent elasticity tensor in there. You know, that's positive definite, right? And you're done. Huh? Okay?
I haven't got it yet, but it's very easily implemented.
Yeah, but I mean, what I want to achieve with this lecture, before we move on, is that you see that theoretically this is how to think of it. So you take you take your commodity space, whatever you have, Q1, Q2, you can put a Q3, right? You just get a 3 vector. And then it won't be a cigar then, it will be some kind, it will be a cigar, right? It won't be an ellipse, it will be some kind of ellipsoid like this. Huh? And this will represent your notion of cost. Huh? Yeah, no, it always works. No, it doesn't always work. If it's going to work, it better be formulated in this way. That's the point. So if you have the substitution effect, and if you have different demands along different axes, which you almost have, always set up a tensor. Make it a real tensor, right? It's got to do all this job, and it's got to be positive, definite, and you can have that, you can see that it's multilinear, right? Huh? So if you have some real number here, and you multiply demand, then you can pull it out. So that's why they say it's bilinear, because you can also do it with that one. Huh? Okay? And once you have that, you can also calculate when this is 0. What does that mean? That the cross price is 0, right? Huh? So they're orthogonal, right? So there's no substitution effect. You can always find these things, right? It's just a question of the eigenvalue problem. You just solve the equation, right? You know all this. That's the principal directions of the inertia a matrix or whatever you call it, okay? So I'm not going to give a lecture on how these things work. The lecture here is just for you to see how you can take that whole apparatus and apply it to your economic problem. Now you know that you can have an inertia tensor, but you can also, and that is linearizing this problem, or if you want this problem, doesn't make much of a difference. But you can also look at the stiffness matrix, right? Huh? And this thing can be generalized also to a tensor. There's no reason why not. Okay? So the convenience yield of one item may depend on the other items. So you have a substitution effect in the convenience yield. Okay? That's when you have some beam, you know, and you're trying to bend it, and then it's you know, so you have the strain like this, and you cause a stress on another surface. This is what you learn in your first year, I believe, right? So you have this stress. That's also a tensor, actually, but you can think of it as a vector if you make it only on one surface.
So the word comes from, right?
What?
Like tensor comes from stress.
Yes.
Yeah, I know for a fact that it does.
Yeah?
Yeah.
I know this, Levi Civita did this, right? Yeah, it's some Italian guys, and he invented the word tensor from tensile, I think, yeah.
Yes.
Yeah, tensile stress, and he called it, that's why I call it a tensor, yeah. The vector is Hamilton, who it was part of a quaternion, right? He called that the vector part. And tensor comes from Levi Civita, I think, yeah, you're right. That's right. So this whole story that I just applied to, and that it doesn't need to be positive definite, by the way. There's no reason the stiffness needs to be anything. You know? All right? So you can go nuts on the convenience yield. What in electrical engineering, what happens is you have the cross effects from the magnetism, right? So you've got this current going through here. It creates a magnetic field, but if you have this core close, it's going to influence the magnetic field of this one, and therefore you get a current there, okay? But you can also have two capacitors, and then the electric field of one is going to mess with the electric field of the other. And according to Kuhn, that's how this board works, right? So you have a little capacitor here, and then another one over here, and you put your finger there, and you mess up the electric field, right? Huh? And then you get this, not mutual inductance, but mutual capacitance, okay? Either way, just keep your mind screwed all right. You can keep all your old formulas, but make this a nice tensor, make this a vector, and make this a covector, you know, and you're done. Huh? Okay? All right. Now, let's have a little bit of fun before the hour is up, or the half hour is up. And I want to just play around and see how far we can take this. So this is one thing you can do. So you remember we had this thing, you know, V1, V2, and I did this, and But now I said, to the hell with this circle. Why do I need a circle? Circle, schmuckle. Instead of a circle, you know what? I'll just draw a hyperbola, you know? And that's what I call length. Now you can say that's ridiculous, but that's not so ridiculous, okay? So he has studied physics, he knows this is not ridiculous. This is actually one of the least ridiculous things that you study. Like, this is just true, right? Yeah? If this is the time axis of this one, we're not gonna worry about that. But there's no reason why you don't know that. And we already looked at this. This is the way compound interest works. So you remember we had these cows, and then they would get calves. But these calves will become cows again. So this thing just goes off like that, right? But either way, at a certain point, you can say, well, this is my original herd. This is my original capital, right? So you will say that this distance is the same as this distance, is the same as this distance, okay? Because either combination gives you the same original, original flow. So this would not be a circle. You would be measuring in hyperbolas.
So
now,
how did you draw the P covector here?
Yeah, it's a little tricky. That's a very good thing.
I'm trying to figure it out.
Yeah.
I don't see some kind of...
No, well, it's a little tricky because you got to do an inversion. So with this thing, it would work, you know, like this, right? So you can do these tangents. But basically what I do is I look at what the orthogonal here, right? And then I move it back to where it's supposed to be, right? Huh? You understand? The construction with the tangent line is not going to work because for the same reason that if I have the vector inside here, it doesn't really work. So I have it inside here because it's, right? Huh? So I need to first flip it out. So I do an inversion, and then I can do it, and then I got to flip it again, right? So it's a little bit. So I was hoping to.
Avoid that question.
Yeah, but I think there's another way of doing it. If you take the conjugate hyperbola, you have this thing. I think you can. Yeah. How do you get these? That tangent construction should work here too, but.
But you can, yeah. It's like the conjugate hyperbola doesn't always come in. Depends on what sort of velocity that you
Right.
move along along a single hyperbola.
Mm.
You always end up on the conjugate hyperbola. That's always the case.
Right.
So it depends on how your vector here is. Also, like.
What if I draw it kind of here? It should work, right? So I'll.
Like, where is
Go from here?
the velocity situated? Is it
See?
also situated from the origin, or is it?
Yeah. Everything is situated from the origin.
Really is there?
Yeah. So this is the answer. So suppose it wasn't as long, it was a short one, right? Huh? Then it will work. So I can just draw this tangent and this tangent. That's the same as doing this. Huh? Okay. So then I would get, this is the covector. Now, the problem is, that's not what I drew. I drew this one. So what I need to do is solve this one and then mirror everything. So suppose I have this vector and I want to draw.
Or invert the distance or something.
I inverted it in my head twice to do this. Yeah. But you see, the problem is the same here. What is here, the covector? Well, it's going to be out here somewhere, right? But how do you draw these tangent lines? You really can't. So what you do is you first mirror this thing in the circle. So it ends up over here. Then you draw this. Then you get this one, and then you mirror it back. That's how you do it. This is how I do it. Huh? But maybe there's a shortcut. But the other way to do it is you think that either way, I'm going to come with something that is tangent to this thing here, right? So I just move that one over because I'm just counting 1, 2, you know. Huh? So I just move it over and then I eyeball it, you know.
Yeah, it's like, I mean, of course, you can see it like a isometric, like surface, right? All the lines, then there's the lines are always locally, they're tangent
Right.
the height, like like there will always be tangent to like what the metric surface is like.
That's right.
So, but it's always infinitesimal, of course, and if you like draw this like huge p vector across multiple hyperbolas, so the p lines will always have a different direction with each hyperbola that you cross.
Yeah. So what you do is you just count the number of hyperbolas you cross,
Yeah,
right?
exactly.
And that's what this p vector does. And then you do it again, and then you get the energy.
Yeah.
Huh? Huh?
For example, like move like tilting more upward.
Yeah, like here, you're not going anywhere.
You're almost moving along the metrics, not accumulating
Yeah.
distance.
Yeah, yeah.
Then
That's a null vector.
the covector, like
Yeah.
for the other one.
Yeah. So that's the null covector. That's the null covector, yeah.
There you go.
And that's called the null cone.
Yep.
So it has zero length, that vector. It is true. Yeah, so, and you know that's true. That's what you call the null cone. So the vectors have zero length, right? Yeah, so this thing will collapse like that. It's like a little harmonica. You're smiling because you agree?
No, I'm smiling because you assume that I know these things.
No. But you know it's called the null cone.
No, I've never heard that term. But it's okay.
Huh?
Do you actually get
But you know that the absolute value of the velocity can be zero. This is speed of light. If this is the speed of light, then the absolute value is zero. Huh?
We don't get hyperbolic spaces.
But do you know?
Yes, general relativity?
No, this is all special relativity.
General relativity.
Yeah.
So what general relativity does is actually it curves space, and locally in every tangent space you have this space.
We're going to get to general relativity, but this is just a tangent space.
Yeah.
That's only kinetic energy. If you change the location where you are, and you put in potential energy, then you get general relativity. You know? Okay? But this is just for kicks. You can also use a parabolic metric. Then it's really simple. You just start counting. This is then your and you go 1, 2, you know? So only the x coordinate matters. Huh? So this is when your capital doesn't grow, right? Huh? It's called a parabolic metric. This is a hyperbolic metric, and the other one's called an elliptic metric. So, but again, it's just a tensor, you know? But this one is not going to be positive definite. It will be positive. It will be have a signature 1, 1, right? So it'll be I don't know how these things go. There will 1 here and a -1 there, and there will 2 zeros if you have an orthogonal one, right? Huh?
This one.
This is the Lorentz metric
This one is
signature.
It depends on the convention.
Yeah.
They do -1 or
Yeah, angle 1. Either way,
or it needs to be 1.
yeah. So you have in one direction you have negative length, and in another direction you have positive length, right? So the point I'm trying to make is, if you think like this, you see this whole circle is not so irrelevant here. You need to have some way of measuring metric, and set up the tensor. The tensor can have any properties you want, and you're done. You can calculate kinetic energy, right? As long as that's your kinetic energy. If that's your economic surplus, then you're done, right? So, and then you can use this theory. You see, that's part of the trick. Relativity has got a long pile of theory. So, for instance, Emil can just use that. He takes this whole thing and he just slaps it on top of it, and then you make all these calculations. Huh? So, this is just another choice of metric. Then, okay, so we know now what anisotropic is. So it changes the direction, right? So instead of a circle, we can have something else. But what we assumed up to now, that the space is homogeneous, that if I take a circle, that this circle is applicable at every point, right? I don't change my meter rods while I will go over somewhere else, all right? That need not be the case, okay? So it may still maintain a circle, but you can get at a certain point a smaller circle, okay? Or it may also change the isotropy so that it becomes a cigar here, You see that? Okay? So then we say this space is anisotropic and inhomogeneous. This is from Arnold's book. Arnold has got a great book. It's impossible to understand if you don't already know everything, right? But once you know everything, you can, that's about, wouldn't you agree that's the right summary? Once you figured it all out, you know he said it all, right? But, no? But that's the, huh? Okay? So here he drew these things. And here, this I got from a little circle like that. When you measure the Earth, they call this an indicatrix rather than a metric tensor. And there, in the early days of measuring cars, there was a guy called Tissot, and it's called Tissot's indicatrix. So this is, I believe, this is the Mercator projection. That's the one we usually use, right? So on the Earth, you would think there's a little metric tensor, so you would think every point, it's a little bit round, of course, right? Because the Earth is round, but like if you've got a really small tangent space, it's flat, so you have a little thing. But that's not how we look at the Earth, because then you have to look at this globe. So what we do is we project it out on a map. And this is the usual projection you see. And you can see that just the projection itself changes the metric. Now, normally they do this by this thing called a legend around here. Huh? But this legend is not really great because they should also give you the legend in the other direction. They usually don't do that, right? Huh? So this legend is another way of saying that you're going to tell me what the cigar is, okay? How you should measure distance when you cruise along here. So if an airplane is going, you know, then you have to take at every point, you have to take this indicatrix, and then you can say how fast it's traveling. You can't just like put your ruler, you know, now. Okay? Okay? So here you see that here it gets all stretched out. So this distance here is the same as this distance. So it looks like you're making an enormous amount of progress here. You're going much faster, but really you're not. Now, from the point of view from somebody who thought the world was this, you see, it may not be so crazy. He just thinks, if I'm close to the pole, my meter rods are just getting longer, right? Eh? Okay, and the other way, my meter rods are getting shorter. I just need a table and keep track of that, and I call that table a legend. Eh? Okay, totally valid, right? In fact, maybe that's what's happening, and just somebody said the Earth was round only because then these things stay nice in circles, and that's the only thing that's special about the Earth being round is that I can measure kinetic energy using the regular square formula. But I can also look at the motion in this thing. All I have to know is that the kinetic energy depends on where I am, right? And the direction I'm going to. All right, so if I'm here, it's going to depend if I go north or if I go this way. Huh? Okay? So then we call this medium inhomogeneous. All right? Okay? This is another projection. I forget whose name is it, but you can see this one keeps the circle the same, equally shaped, but the area, you know, now is changing. So you can see here, yeah, so here the velocity just goes up uniformly. Huh? This one, everything is squeezed. You have also these maps where the area is the same, but then they need to squeeze other things. You can't keep both. You can't keep isotropy and homogeneity because the Earth is not flat. All right? Okay? So this indicatrix, you can say, well, really, it's just a bunch of measurements on what these airplanes are doing, and we don't like it that this airplane seems to be speeding up like there's no tomorrow over there. Or in this case, it was these people with these boats. So you know what we're going to assume? We're going to assume our boat goes with constant speed, but that the distance is changing, and we'll just put a legend underneath here telling you how the distance changes, you know?
Isn't the bottom used more?
Maybe this is the, no, I think this is the one. No, yeah, this is the Mercator then?
Yeah, the bottom map,
Yeah.
because I recognize the shape of Greenland.
Yeah.
Yeah, Greenland's like ridiculous.
Yeah, you're right. This is probably the Mercator.
Yeah, because that one is conformal, so people their angle
Yeah. The plot, yeah.
or both.
Yeah, you see this one is conformal because, yeah, because you navigate. You can navigate with the stars.
Totally.
So you got to see the direction. You have your plumb, you know. Huh? That's right. Huh? You can see that's not a nautical nation, Belgium. Huh? No. Huh? But this is the one they use basically because they could keep a certain course. You know, so many, you know.
And also has the added benefit of making South America and Africa look really tiny.
Yeah, I don't really think they're worried about that. You know, because yeah, it makes it look tiny, but this one too, right? Huh? A little bit bigger. No, yeah, this one is equal area because this area is equal to that,
Yeah,
right?
That's
So this is the politically correct map where you think that importance and area are the same thing, right? Huh? This is a political correctness where with direction, and this will be the good map, right? You just can't have it all. But what for us is important here is that really it's a choice here. What are you going to do? Right? So you can say my economic system just happens to be this. Or you can say, no, I'm going to put it on a globe and then everything looks regular. Mathematicians call this also regularization. So there are papers about the Kepler problem with hyperbola, and they call it the regularization of the Kepler problem. So you start looking at it as a Euclidean problem, okay? And then here you see what Arnold does with it. So at any point in his commodity space, you will draw this thing, but here he could draw another one, and if you connect them all, you get the wavefront again, right? So you can see here there is the ray, but this is another ray, and from these rays and these indicatrixes, you can make the wavefront. So you can look at this particle as moving through space, or as a set of waves just moving out, okay? All right?
The wavefront is sort of a furthest.
Yeah, in a particular time.
Yeah, exactly.
Right. That's right. That's right. And that brings me to my last slide. What's going on? Yeah, which is Hamilton's principle. So all that Hamilton's principle is you give a name to this indicatrix, this little thing, right? And you just add them all up as you go along a path. So this is going along some path, okay? So there's a total distance. This thing is called the Lagrangian, and this is what you call the action. So this will be some running cost, and this will be the total cost that you make, okay? And then what you try to do in equilibrium is you find that you want to minimize the costs. So you want to go along the geodesic, the shortest distance. That's the minimum cost required, okay? Economists also call this the expenditure minimization principle, and in mechanics is known as the action minimization, stationary action principle, or Hamilton's principle. So you minimize this total length. And the length is given by something called the Lagrangian. Now, what is this Lagrangian? Well, in the simplest case, it's just equal to the kinetic energy, right? That's for a homogeneous medium. And then if you have Newton's case, you go along a straight line. You know, both speed and direction are the same, because the shortest distance is then just this, right? Because your indicatrix is just running along like this. Huh? But you can also have it that this is kind of complicated. You can also have a straight line or a curved line, or you can say, well, it will also depend on where you are. And that's your convenience here. Those are the benefits that accrue to you. And that will make that this indicatrix will, will start depending on where you are. Okay? So you'll look at the net running costs, or the net profits or whatever, and things may look quite differently. Huh? Either way, you get this picture that Arnold has of the particle going along the ray, and at any point there's indication. Then he looks at the orthogonal direction, so you know he does this thing, right? And then he moves it over. Huh? He actually doesn't use one forms because not that he doesn't know it, it just thought that people wouldn't understand it. Huh? So he has the vector p, but he says the front moves along with the momentum, right? And then how does it move? Well, how the indicatrix changes when you change phi. This is just a definition of momentum. And out comes this picture of particles moving, and the question you do is find out the minimum to reach a particular point. For us, of course, this is the cost wave, you know. The cost, it just comes as this wave over you, you know. You can count wavelengths. Those are probably business cycles that you're counting or something else. I didn't want to make that all part of this lecture. This is just the idea that you have as a metric tensor measuring the substitution effect and blah, 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 and then carried out to that extreme, right? So from this one idea, we can get the entire equations of motions or the entire activity of the guy by saying all he's doing is minimizing costs. And it just so happens that that coincides with Newton's description when there's a single point mass that has a mass m in all directions, right? But it's much more general, right? We can solve anything we like, huh? Okay? And we can, you see, these are some cost, and these v, these were the benefits. So you can see that what this thing does, it takes your running costs and it subtracts whatever benefits are stored. But that's not it. You can also disrupt the friction terms. You can, you know, all kinds of forces may be acting on it, right? All kinds of wants. You know, this is just a mass spring system, not even dampers, okay? But the,
You could add extra terms to that.
Of course, and people do. Yeah, if you have a damper, you're going to add an extra term.
They just add a D term.
Yeah.
They call it the sort of the damping. And
yeah.
Yeah, and within Lagrangian mechanics, that's okay. Within Hamiltonian,
it's also okay, but you need to go to an extended phase space. Yeah. And that's what this is. You see, because here he measures Q and he measures time. Then he has an orthogonal direction. Then he has a price belonging to Q, but he has a price for time too. And that is the Hamiltonian, or the energy. That's the price for time. Okay? So you will see that the total cost will change as soon as you buy some more stuff. But in the meantime that you're spending buying this, you may derive some benefits that you have to subtract. Okay?
Because without the time integral, that damping energy cannot be
No.
included, right?
No. So, but this is for a later lecture, if I ever get to it, how to include that correctly in a Lagrangian. All you need to see now is that it's just a picture that gives you what you see. Newton tells you how to move forward a little step and then a little step and a little step in a very special situation where you have one point mass the same in all directions, okay? This thing tells you, all right, forget about the little steps. Where will I be after this? Now, I minimize this, and then I'll work my way back, I'll see it's the same. Except when I can generalize. I can have different directions, this, I can have angles, I can do all this crap, right? Huh? So it's the generalization. Huh? For economics, Newton is a description of economics in terms of demand and supply. At this point, I'm demanding so much and I'm willing to pay so much for it, and blah, 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 blah. I have to talk myself through it. But I can also do economics and say, well, you know, what I'm going to do with my whole life is I'm just going to maximize your utility. Okay, I'm done. Bye-bye. You know, see me act. You know? It's a totally valid description that leads to exactly the same thing. Okay? And economists have these too, and they correspond to our Newtonian and Lagrangian description. Okay? But they never really show how they're the same, but within this framework you can prove that they're the same. Huh? And in a certain way, the ray description, how you move forward, that's more Newtonian. And the wave front is more Lagrangian of Hamiltonian. You focus on the price, you know, where you want to be, right? How much cost you want to make, the expenditure minimization, not demand. What am I asking for right now, you know? Huh? But what are my total expenses, and how do I minimize this? All right? So there's a different perspective. And this minimization we present as a problem in minimum distance because it's so intuitive. Why? Because we think of this demander like a particle in space doing something, and what it naturally does is minimize the time it takes to do something. That's what light does, or, huh? Okay? I went 5 minutes over time, so I'm gonna stop the, yeah, you can stop the recording. And then